Section 4.4 continue. Now let's move on with and probabilities with dependent events. In our previous example, each friend put their marble back after making a selection. When that occurs, that is called sampling with replacement. And we mentioned that a little bit before. But what if they kept it? How would the previous probabilities change if each person kept the marble that they selected? So we're going to go back to that game in example 2, this time taking into consideration that each person keeps the marble that they select. And we have pretty much the same questions. A, is each friend's selection of a marble an independent event? Well, now that they are keeping the selection, it changes and it's going to alter what's going to happen on the next person's turn. So if the first person picks a red marble, the next person only has 4 red marbles to choose from. Whereas before, when they were putting the marbles back, each person had the exact same number of reds, blues, greens, and blacks to choose from. So this time, no, the selections are not independent. Okay, B, what is the probability that everyone selects a red marble? Now before, with an independent event, all we had to do was figure out what the probability was to select a red marble for anybody, and we were able to duplicate that for everyone. But here it's going to be a little bit different. So I want the probability, well, we know what we're finding. We're saying the first person finds red and the second person red. That part's the same, the notation rather, and the fourth person. But think about the probabilities. That first person has all the marbles to choose from. We know that there are 13 total, and there are, if we go back to that pool, there are 5 to choose from altogether for that first person. But with the second person, there's no longer 13 marbles to choose from. How many are there now? There are only 12. And we're going to assume that first person picked red, because otherwise we don't get the chance of everybody picking red. So if that first person picked a red marble, how many red marbles are left? Well, now there are only 4. That outcome is affected by what happened on the first trial, so that's why these are not independent. Now let's think about the third person. The first person has a red marble and kept it. The second person has a red marble, or we're assuming has a red marble and kept it. Well, now how many marbles do they have to choose from altogether? Only 11. And if we're assuming that those first 2 people have red marbles, now there are only 3 red marbles to choose from. And if you kind of get the hang of the pattern now here, the fourth person only has 10 marbles to choose from altogether, and of the red, there's only 2 left. So with independent events, that probability stayed the same from trial to trial. But with dependent events, it's changing based on what happened previously. And if I multiply these together, 2.00699 or 0.007 if rounded to 3 places after the decimal, this even works out to a fraction 1/143. Okay, and C. What is the probability that no one selects a black marble? So we want the probability that no one, first person doesn't select one, and the second person doesn't, and the third person doesn't, or does not rather, and the fourth person does not. Okay, so we learned from the previous example that there are 13 marbles total, and 12 of them are not black because they are green, red, or blue. Now, whatever marble that person picks, we don't care what color it is as long as it's not black. the second person is only going to have how many marbles to choose from? Just 12. And of the non-black marbles, there's only going to be 11 of those left. For the third person, now they only have 11 marbles to choose from. And for the non-black marbles, there's only 10 of those left. And for the fourth person, they only have 10 marbles to choose from. And of the ones that are not black, there's only 9 of those left. And when you happen upon a problem like this, I would encourage you to go ahead and simplify rather than punch all of this in your calculator. So if you notice, we have quite a few things canceling, and we are left with 9/13. So it's a little time consuming to punch in all those fractions when you can easily see that a numerator cancels with the denominator. 9/13, or as a decimal, that would be 0.69, rounded to 2 places after the decimal. So just to compare between independent and dependent, for that second event, we got 0.02 before, and down here we got 0.007, so a lot less likely. If for 3, not getting a black marble, we got 0.72, but down here was 0.69. So whether the events are independent or dependent changes our answer. So when we're looking at a probability problem, we do want to ask ourselves, is sampling with or without replacement, which is going to tell us whether the trials are or the events are dependent or independent. Okay, so noting the changes we had to make to calculate the above probabilities, our formula for the multiplication rule changes slightly. So we still have this probability of A and B, but we had to take in consideration we're still going to multiply by probability of A, but probability of B gets a little extra here. We do take the probability of B, but we have to pay attention to, given the fact that A has already occurred. So we're making that assumption, and that's how that second probability is changing. That's when we write it that way, the probability of B given that A has already occurred, that is called a conditional probability, because it's conditional on what happened in a previous event. It's denoted P of B given A. That bar there is red. Probability of B given A. So that's a conditional probability taking into account something else has already occurred. So that changes our multiplication formula here. Multiplication rule for dependent events. The probability of A and B is equal to the probability of A times the probability of B given that A has already happened, and that's the same thing if we use it with set notation and the intersection. Down here at the bottom though, if A and B are independent events, the probability of B given A is the same as the probability of B because it wasn't affected by A, and then we get back to our previous multiplication formula. So all of this works together. Let's try example 4. The local animal shelter reported that it currently has 24 dogs and 18 cats available for adoption. 2 families come in to select an animal for adoption. What is the probability that both families select a dog? Well, here we're looking at, well, let's say this. We'll define our event. Let D be the event. A family selects a dog. Okay, so I'm looking for the probability that family 1 and family 2 selects a dog. But what I have to ask myself is, are the selection of a dog from the first family, is that independent of the selection of a dog for the second family? Well, they are dependent, because if there's one cute dog that all the kids fall in love with, if the first family takes it, well, now the second family has to make a different choice. They are not selecting from the same pool of dogs, so these are definitely dependent events. So because of that, when I go to write out my probability, is the probability that the first family selects a dog times the probability that the second family selects a dog given that the first one has already selected. Okay, well, what is the probability that the first family selects a dog? Well, first we have to know how many possible choices there are. There are 24 dogs and 18 cats, so that's a total of 42 animals to choose from. And if the first family is interested in a dog, the probability of selecting one is 24 out of 42. Now remember, for the second family, we're going to assume that first family selected a dog and took it home. So for the second family, now how many animals do they have to choose from? Only 41. And they're also interested in a dog, but there's one less dog to choose from, so there are 23. So 24 out of 42 for the first family, total 42 animals, 24 of them are dogs. But for the second family, there's one less animal total to choose from, so there's where our 41 comes from. There's also one less dog to select from. Let's see what we get here. In fraction form, I get 92 over 287, or as a decimal, 0.32055, and rounded to two places, that would be 0.32. Okay. Treating dependent events as independents. Usually, if we're sampling without replacement, just like with the marbles and selecting the animals from the shelter, then we can say the simple events are dependent, because we take one away and now the selection has changed. The exception, however, is when the sample size is relatively small compared to the population. A good rule of thumb is when the sample size is no more than 5% of the size of the population. If that's the case, we can assume independence. In this case, we use the same probability for each trial rather than adjusting for the previous event. So what's basically going on here is if the sample is really small compared to the population, even if the events truly are dependent, you take one away and there's one less and the selection changes, what happens is because the sample is so small compared to the population, that one item that's taken away doesn't affect the probability very much. The change is so small that we just kind of ignore that they really are dependent events and we treat them as independent. So take a look at example 5. In a production run of 1,500 widgets, it is known that 5 of them are defective. If 3 widgets are selected at random without replacement, what is the probability that all 3 are good? Okay, so let's let G be the event that a widget is good. So the probability of G is 1,495 out of 1,500. So there were 1,500 made altogether. 5 of them were bad, so we know for sure 1,495 of them are good. Now, truly, if I take one, we're picking these 3 widgets at random, and we want the probability that all 3 are good. Yes, these are technically dependent events because I would take one and I'd keep it, and so then I'd have 1,499 to choose from, and I'd have 1,494 that are good. Very, very true. But because that probability is going to be so, and let's actually look at it. So the 1,495 divided by 1,500, and this is just for example's sake, is 0.99667. But if I were to stick to my guns about it being without replacement, I would say the probability of the next one being good would be 1,494 over 1,499. Well, that is 0.9966. This one goes, the decimal places, the 6's keep going forever, and this one is 66 Chp4Sec4b. But notice how small the difference is. I mean, it's not until the, fifth or sixth decimal place that we even have a change. So because that's so small, we don't bother to keep saying, okay, and then on the third trial, 1,493 over 1,490, it's too small and it makes the calculation cumbersome. So instead of doing that, we just treat it as independent. So to say the probability that the first one is good, so essentially what we're finding, the first one is good and the second one is good and the third one is good. Assuming independence, we can just go ahead and say multiply the probability that the first one is good times the probability that the second one is good times the probability that the third one is good. So we have 1,495 over 1,500, and I'm just going to raise that to the third power. So here, instead of doing these other calculations, we're just going to assume independence. And it's not wrong at all if you chose to do it the other way. It's just we can save a little bit of time and not worry about such complicated numbers. And I get 0.990033, so rounded to 2 places after the decimal. That would be 0.99. And that is it.